All right, hello everyone. This is Groundwater Talk Live. I'm Tom Ballard, and today we have a great guest. We're going to talk life cycle economic analysis of water wells with Marvin Glotfelty of Clear Creek Associates. We Before we get going, I always ask everybody to like, comment, and share. We answer all the comments that we get, and it gets the word out there. So we appreciate that. If you like the show, just share it with your colleagues so today we have Marvin Glotfelty with us, and uh, for the one or two people out there that don't know Marvin, he's principal hydrogeologist and co-founder of Clear Creek Associates in Arizona. He's got over 38 experience in the design, installation, rehabilitation, and decommissioning of about 1,000 water wells in the southwestern U.S., so a lot of experience. He's a registered professional geologist in Arizona and California, and he's also a licensed water well driller in Arizona, so a unique combination there. He was National Groundwater Association's Distinguished McEllhiney Lecturer in 2012, which is actually where I first met him. I'm sure Marvin doesn't remember that, but at the California Groundwater Association is where I met him there, and he talked on this topic, and it really changed my outlook on things. So he's given over 100 presentations. In 17 states and 5 countries, authored more than 30 publications, including his book, The Art of Water Wells, which I highly recommend you pick up. I bought a bunch of them when they came out and gave them out to folks. Great book. He writes a quarterly article titled The Art of Water Wells for National Groundwater Association's Water Well Journal. And last but not least, he is the 2023 recipient of the National Groundwater Association's Ross L. Oliver Award, which is really their most prestigious award. Uh, but through all that, Marvin remains a great guy. He's always willing to talk to folks and share his knowledge. So we really appreciate him, and he's just, you know, somebody in the industry that's a great resource. So welcome, Marvin, and thanks so much for agreeing to come on the show. And you have contributed so much to the industry, but I will tell you the life cycle economic analysis of water wells. When I saw your McEllhiney talk in 2012, it really changed my perspective on things, and I have been an advocate of that ever since. You totally convinced me. So
Well, thanks. I
I'm
appreciate
glad you
that.
could come on and talk to us about this. So so let's kind of dive in, and we can run through the presentation, and then I got some questions we can ask, but a little more background on you. What are you working on these days? And
Well, I'm like all of us. I think I'm busy, busy as can be. Um, we are continuing, of course, here in Arizona, in the entire Southwest, and in many other parts of the country, we've got conditions. So the surface water supplies upon which we relied, in case of Arizona, Colorado River, have been limited. Um, Now, we had a good wet winter last winter. We're hoping for one again this year, but as us hydrologists know, one wet winter doesn't solve a drought, and so we'll see. But that means that everybody's focused on beefing up their previously ignored groundwater systems. And so that's a good thing in general, but it makes all of us very busy. The drillers in this area are very busy. The hydrogeologists, like myself, are very busy. So that goes to every sector: municipal, mining, industry, everything. So, and there's a lot of interesting far flung projects like lithium mining in many remote areas, zinc mining. The people need resources that were always there, like copper, but other newer things. Lithium because of all our cell phones and electronics. And so, yeah, it's an interesting and busy time. And I'm glad that to have received the invitation to re-talk about life cycle economic analysis because I mean, it's old, you know. It's like me, it's old, but it's a good topic, and it still applies. And so as I go through it, and I've abbreviated this, you know, the actual McEllhiney lecture, I did it in 2012, so that's now over a decade old, but the concept still applies. And even at the time when I gave it in 2012, it was based on 2011 data, and even then, you know, some folks said, hey, I just drill for domestic wells and windmills and things like that. What does this mean? Because you're looking at these huge wells. Well, it's a matter of scale, but the principles still remain. You know, the fact is, are you going to focus on the cost at the moment of well installation, or are you going to look at the whole life and look at that value? So that's what it boils down to.
Yeah, we live in a low bidder world, which is something I think about every bridge I drive over. you know, you
Yeah,
know, you got to think about that as, this bridge was built by the low bidder, So,
yeah.
and so,
So
yeah,
and also true with water wells. You know, you see them and shake your head and try to and yet I find that the preponderance of drillers and hydrogeologists want to put in quality. They just need to allow that. So this message that what we really should do is share it with the general public when the opportunity arises, because that's the folks that really need to understand that what's more important than your water supply. So you really should have some quality involved there, and it makes a difference depending on what you're doing. That changes everything. If you're going to dewater a site for a temporary construction project, that's a whole different thing than relying on water for the general public for forevermore. You know, two different, complete different ends of the spectrum.
I totally agree, and it's just kind of getting people reoriented in that thinking, and it's just yeah, and I'm kind of in the space. I mean, my specialty these days is kind of wind down my career here is that I really work on water well diagnostics is my main focus, and you just see certain patterns and trends out there, and so many of them are construction related, not building things properly and trying to do it cheap and like I say, the low cost bid, and you run into problems down the road and you end up, spending a lot of money to try to fix things or just even having to replace wells that should, that failed far before they should have, and just because of the construction methods, and then we run into well seal problems. That's probably a huge I mean a lot of things we can get into, but so many problems related to well construction that shouldn't happen, I guess, and so that's why this message is so good. So, all right, well, I can. We kind of had a glitch. Marvin can't share his slides, so I'm going to share them, and we will kind of go through those. So if you want to dive in, Marvin, I'll bring this up here, and
So yeah,
you
so
can
here's
just
the
tell me
title.
when to switch the slides, and we'll do it that way. So.
Very good, will do. So the life cycle economic analysis, this is an abbreviated version of what I did back in 2012. Go ahead to the next slide. And there are three common types. This looks at steel types for well screen primarily. The first one, low carbon steel, also known as black steel, mild steel. It is the least expensive of the three steel types we look at, and also the least corrosion resistant. Now, in this talk, we don't really focus on PVC casing, but that could also be included in a site-specific life cycle economic analysis. But we won't talk about that today. The next steel type is high strength, low alloy, also known as Corten or Kywell steel, or the old cable tooler term for hard red steel, same stuff. And what you see a photograph there of is the U.S. Steel building in Pittsburgh, which is made out of this. And what it does is gets a veneer, a protective veneer on the surface of the steel because of oxidation. And that, of course, oxidizes very quickly, gives the red color, but then it further protects against greater corrosion. So it's more expensive than low carbon, but also more has a greater longevity. It lasts longer. And then the third steel type is stainless steel. Of course, the most expensive and the most corrosion resistant. Now, there's different types of stainless steel. There's, 304, 316, etc. In this talk, for the cost we're talking about, it's all 304, the least expensive and most common type for well screens. So these are the three costs, and we want to compare them to one another. So let's go to the next slide. And here's another consideration that we need to add to the corrosion resistance, and that's the tendency of these screens to accumulate biochemical scale accumulation. So in um, in many locations, we might have a low carbon steel at one location and a stainless steel very nearby. And so how do we compare those? It may have been installed at different times in slightly different hydrogeologic environments and by different drillers and so on. But in a number of wells in the El Paso, Texas area, there are these wells with this interesting design where they put in stainless steel louvered well screen alternating with low carbon steel blank sections, back and forth, many different places. So where the red arrow is there is an example of what we're looking at. We're just above in the video camera, above the depth where the well changes from stainless steel louvered screen into blank casing. And what you see there is some not exactly clean as a dinner fork, but pretty good looking stainless steel screen. And we click to the next slide, going down just 1 foot, and we see that the blank section with the low carbon steel has centimeters thick of scale accumulation. So the bugs that deposit that scale really like the low carbon steel much better than the stainless steel. And we see this over and over and over repeated. So the point of this is the economics of a well is not only how long it will last, it's also how much maintenance in the form of cleaning the scale from the well is going to be required over its life cycle. So that's why we're including this as a consideration. So we'll go to the next slide. And here's the math on this. Click one more time, and we have the math. So this is just from a website that gives the cost to pump water out of the ground. And then you can see in there that we have the cost per hour is the gallons per minute times the lift, the total dynamic head, times the constant, and times the cost per kilowatt hour, all that divided by another constant multiplied by pump and motor efficiency. So that means that if we have to lift that water higher, we're not only going to move off of the pump curve and probably get fewer gallons per minute, but we're going to be spending more energy dollars to get that water to the surface. So that can add up certainly over a life cycle to be really tens of thousands of dollars per well. So click to the next one here, and we'll see what I incorporated in this economic analysis. I've done this a couple of times, but for this one, what I did in 2012, gathered the information for it in 2011, and I looked back in time at 70 existing wells. Go ahead and click, Tom. So we had 70 wells, and you see where they are within Arizona. 8 different drilling companies, 5 different hydrogeology consultants, and spanning an 18-year period. So we had a pretty good record looking back in time, and what that provided us was some understanding of the way costs varied over time, looking back. Well, we also wanted to look forward in time, and that's the life cycle economic analysis. And for that, we averaged some recent year, within the last 5 years at that time, O&M costs, and that was provided by the city of Phoenix. So we knew we had actual, reliable, real-world costs. We looked at the current, 2011, material costs, and we incorporated that in there, and then the actual drilling costs. Go ahead to the next. And here's the 3 imaginary wells that we compared to one another. So we wanted to keep them focused only on the well screen differences. So we have the same depth for all the wells, the same diameter for all the wells, and the same aquifer conditions for all the wells. So it's a 18-inch diameter well, 1,200 feet deep, with a 400-foot static water level. And this is because it's typical scenario for my area. It might be different in different places. And so if you were to do this in your local area, you'd want to apply the representative scenario. And then you notice that they all have low carbon steel upper blank well casing, but the one on the left has a low carbon steel screen, the one in the middle a high strength low alloy screen, and the one on the right a stainless steel screen. So we can now compare these to one another and look at them through a life cycle. So we have assumptions that we apply to all three of these wells. Let's click again. And the general assumptions are, first, we're looking at a 75-year life cycle. If we had a power plant that had or an industrial facility that had a 20-year facility life, we'd look at a 20-year life cycle. Or maybe if we want to, we could look at a 100-year life cycle. It's a determination you want to make up front because it does make a difference. Next, we assume they all pump 1,200 gallons a minute. Next, that they're being pumped 65% of the time. This is real world from the city of Phoenix. Next, specific capacity, we just made a reasonable assumption for our area that it starts out at 20 gallons per minute per foot of drawdown. And then the next. And so we have the static water level at 400. And we, just to be, put it under a stressful situation, we assumed a regional water table decline of 3 feet per year. That used to happen in the Phoenix area, stopped happening after we imparted the Groundwater Management Act of 1980, but still we went ahead and applied that to be conservative for this study. Next. And then we wanted to be real world, so we added a little more pressure to the pump. So it has to pump an additional 50 feet, not just to the land surface. That's applied to all three wells. Next. Electricity, it can vary. It costed at that time 8 cents per kilowatt hour, so that's what we used. Next. And we used the median value from that previous equation for pump efficiency and assume they are replaced every 10 years. And then the last one is the motor, the same. We used the efficiency from the middle of the equation I showed you before, and then we replace those motors every 10 years. So this is what's applied to each of the wells. And there's also assumptions for each of the individual wells. So let's go to the next one. Click again. And here's low carbon steel. So for low carbon steel, based on the experience in the Phoenix area, we assume that every 5 years there's scale accumulation that makes the specific capacity drop by 25%. And then after that 5-year period, we clean the well and it gets 88% better than what it had been before. And this is just based on a lot of data that we looked at for the local area. Click again. And we have high strength flow alloy. For clogging, it's pretty similar. So we just assumed that it was 6 years instead of 5 years to get that drop in 25% efficiency. And when we cleaned it, we assumed it did a little bit better, 90% instead of 88%, not much better. The big difference is it doesn't corrode as fast. So it lasts 40 years instead of 25 years and must be replaced at the end of each of those periods. And then stainless steel, the last one, it doesn't scale up much. So we assumed that to lose 25% of its efficiency, it took 30 years, and then after being cleaned, came back to a 95% of the previous level, and that the well would not corrode away, it would last the full 75 years. So these are the assumptions that were embedded in this. So got to be sure that you have full buy-in to the assumptions when you start an analysis like this, and we were very detailed and extensive on outreach to operators, etc., when we first did this. Next. So here's the way this graphs out. Go ahead and click, and you can see that this is for low carbon steel well. Starts at 20 gallons per minute per foot of drawdown. So on the vertical axis is the specific capacity, and on the horizontal axis is time. So we lose our specific capacity after 5 years, 25%. So we've gone down to 15 gallons per minute per foot of drawdown. Go ahead and click. Then we clean the well. It improves and then degrades again for the next 5 years, and the next 5 years, and the next 5 years. So on each of these cleaning cycles, you can see that we were 88% of the previous specific capacity. That's where we came up with those numbers. Then after 25 years, we're now going to replace the well. So we replace the well, and it is assumed to provide a performance 40% better than the previous highest specific capacity. So go ahead and click again, and you can see that where that comes from, and click one more time. It shows where we come up with that. So we take the last specific capacity, and 140% of that value is where we assume the starting point is for the second well. Go ahead and click again. And now we have the second and the third well over the 75-year life cycle for low carbon steel. So this is where we came up with all this. And then click again, we have high strength low alloy. It's similar, except that it takes 6 years instead of 5 years between each cleaning cycle. And we can go all the way till the 40th year before we replace the well. So we only have 2 wells in this 75-year life cycle instead of 3 wells for HSLA screens. And then lastly, click one more time, and we have the stainless steel wells. It lasts the entire 75 years and only needs to be cleaned every 30 years. So this is the way it plots out, and you can kind of see from this plot, because the area under each plot is the energy use. So there's going to be less energy use when the specific capacity doesn't drop as far down as much of the time, and more energy use for like the low carbon steel where it's really degraded a lot of the time over its life cycle. So let's go to the next slide. And here's what unfortunately everybody focuses on, the low bid mentality. So we took these values. Unfortunately, wells don't cost this anymore. They're much more expensive. But back in 2011, based on a dozen low bids from the previous 5 years, here's what wells costed of this design. And we used for all these wells the current 2011 numbers with a contractor markup for our cost estimate. So this is where we came up with these numbers. We did not include land acquisition. We assumed that the owner would already have land, because that complicates things so much. But we see here low carbon steel are roughly $512,000 for one of these wells. This 1,200 foot deep, 18-inch diameter well. HSLA about $567,000, and stainless steel about $776,000. So we have more than $250,000 difference between stainless steel and low carbon steel just because of the difference in the screen material. So that varies year by year, and it varies over time, and it varies depending on the supply and demand. But generally we can say, okay, here's what it is, and we can apply these numbers for today and re-look at it. It's going to be on that trend, though, that these costs, you start higher with stainless steel than you do with mild steel or even HSLA, but will it pay for itself? You know, that's the question we were asking ourselves. So go to the next slide. And we had some other cost considerations because we wanted to be complete. So let's throw those in. We started with the well construction cost. Next one. We added some supplemental things just to be complete: sound abatement, fluid disposal, demolition of existing equipment. Next. So the consultant cost. The hydrogeology is a lower cost. The engineering is a higher cost. I never figured out why that is, but it tends to be the case. But we applied those. Next.
Geologists are cheap.
Yeah, I guess so. We're low bid. Yeah. Yeah, next. So the well clean, we put those in each time, and what we did was alternate between mostly brush and bale, sometimes acidizing, you know, just alternately. For the stainless steel, because it was less common, we always applied the cost for acidizing, which is much higher than for brush and bale. Next. O&M labor cost. That's pretty much the same for all wells, but we applied it. And next. Pump and motor replacement. That happens every 10 years. We do assume that for when the first years of a well, that we don't apply any wear and tear, because there's probably going to be a new pump and motor. So for those wells that are being replaced more often, there's less pump and motor costs. So that kind of actually offset things slightly, but it's real world. Next. Electrical costs, that turned out to be a big one when you're looking at it over 75 years. And then the last, oh, we go to the next here. Okay, so here's the punchline. After 75 years, if you look at that top row, up beside the little cartoons of the wells, you have again just a repeat of the construction cost. So we started with the stainless steel on the right-hand column being the highest cost, but then in the first row, you see what when we add up all these other costs over 75 years, the low carbon steel well costs about $15.7 million. The high strength low alloy well about $14.5 million, and the stainless steel well about $12.4 million. So if we oversimplify the math and just divide by 75 and look at per year well cost, you see the second row, and that means that at the end of 75 years, as shown in the third row, you spend actually more money by $3.3 million for a low carbon steel well than you did for a stainless steel well. And when you compare it to HSLA, it's over $2 million more compared to stainless steel. And so the last row there is the cost per year. And so we can work out, okay, what's the payback period based on oversimplified math. In other words, we're just dividing by 75 years. We're not looking at it year by year more detailed because that was going to be a lot of extra work that I didn't want to do at the time. So go ahead and click again. And we see that for HSLA compared to stainless steel, we see a payback of about 75 years. And one more time, for low carbon steel, the payback is about 6 years. And that was good to see because that was consistent with some previous studies I did. Go ahead and click to the next slide. And you can see that I first did this kind of a life cycle economic analysis for a private water company based on 36 wells back in 2003. I repeated it with a larger database in 2008. And then for the McEllhiney study, I did it once again based on 70 wells. And you can see that the payback periods are very consistent, just a little bit of tweaking with the input data on each of those analyses. And so I'm feeling like this must be a reasonable study. And actually what I've done is gone to economic people. I'm not an economist, and asked them if this is the right approach and everything, and did have it confirmed that that's the proper approach to use for this. So I think that's the last slide. If you can click comments, yeah. So the only you know, the walk away with this that I get is that don't think about just the cost of the installation of wells. Think about the entire life cycle and realize that this was for Arizona, for municipalities mostly. What if you're in Tennessee? What if you're looking at a household well? That might be a completely different scenario, but you can still look at what's the life cycle cost, and there's other data that you can input, and you may not know it, but you can make reasonable estimates. And this is information that once you package it together, you can then roll it out to the well owners. They don't know. They just think, wow, this costs more, and they all make water, and then they don't even know about scale accumulation and things like that. So the energy costs is the deadly one, I find. People are paying way more in energy costs and maintenance costs, and they think, well, I got the cheapest well. It's the same one. It's just as round as all the others, and it's dark down there, so I don't know what's going on. So that's the problem. So I think that with that, I'll be glad to field any questions from folks might have.
Yeah, I haven't had any pop up here, but I got some. So, you know, I want to. We really get into this low bidder mentality and the lowest cost up front because, you know, when people are talking about 75-year lifespans, you know, it's kind of like, well, I'm going to be retired long before then. So it's, you know, so it's probably not going to be my problem. So how successful are you at convincing water utilities to look at this? I mean, usually, and I see a break point between some of the bigger water utilities and the really small ones that are really pinching pennies. So it, I mean, this really resonates with me, and I kind of preach this to everybody I talk to. But you know, do you get resistance out there to this?
get a surprisingly high amount of acceptance.
Right.
Now, you're right. There are some smaller, mostly entities that like to go cheap, and they say, "This is the way Grandpa did it. I'm going to do it this way too." That's fine. But when you are talking money, people tend to listen. And you're right. That used to be the "not in my backyard" mentality. Now it's "not in my term of office." And so if they think if it's going to be go terrible after they retire, they don't care. Well, for some entities that might work, but for municipalities, for public water supply, for anybody in the power or mining industry, because that's critical. Water is critical. Without water, everything shuts down. So those guys take it seriously, and those guys in my region have almost entirely switched to stainless steel screens. Now they still go with mild steel upper casings, sometimes HSLA, sometimes low carbon. And that means there's a need for a dielectric coupling, a dissimilar metal connector. And that adds some complexity, but it's doable. And then in some cases, it doesn't make sense. There's a broad variability. And so I find though that it has worked out pretty well, and really the most driving factor was those El Paso area well videos, so they could see that there is going to be a difference. So it's not only the cost of the rehabilitation, but that energy cost in between cleanings when you're spending more energy dollars to pump the same water. That's what really has been the motivation I think for folks.
Yeah, and it's something that not a lot of people think about when you're constructing well is the electricity cost to operate that. So that's actually a very good point. So,
It
because we
really
think
is.
about the construction costs and all that, but the day-to-day operating costs really factor in there. So, all right. So according to the U.S. EPA calculations on life of assets, they look at um, oh, somebody said the comment section is not active. So, um, on, huh, I don't know how I did that, but all right. Well, we're just gonna have to go with it. I don't know what I did with. I usually set that up, so I don't know what happened. Thanks, Russell. Um, so, according to the U.S. EPA, the asset life for a water well is 40 years, which seems to be, kind of outdated and probably based on mild steel. But what type of? It seems like we're looking at stretching the lifespan on our wells more and more. What kind of, with your approach, what kind of realistic life can we expect for a water well? I mean, and I know there's a lot of different factors, corrosion of the groundwater and a lot of different things in there. But what's realistic? Can we look at 80 years, 100 years on these things if they're built right?
Yeah, we can. And actually, the values I used in the life cycle economic analysis were the most typical for the Phoenix metro area. But there are wells that are HSLA, old hard red steel, that are 100-year-old wells in our area as well. So even though I was using 40 years for that steel type, there are other examples where it's been around even longer. They're not as common. But so what about other parts of the country? When I was traveling around giving the McEllhiney lecture, I had people in the north central part of the country, I think it was Michigan or so, tell me that they got 25 years out of galvanized wire wrap steel. And I told them that in Arizona we would probably get more like 25 minutes out of those. Galvanized wire wrap is just not used around here. That's not that it's bad. It's just not used around here. So we have different waters. We have different aggressivenesses and things like that. Salinity, Langolier index, all those sort of things vary. And so what's the right answer? There is no right answer. But whatever it is, that's based on a couple of things. The local hydrogeology is one, but also the use. Are you using a well occasionally or frequently? Okay, actually, people, that's where it's a little bit counterintuitive because people think, well, I didn't use the well as much; it must have more life left. It's the opposite. If you have stagnation of the water, then you can have a lot of biochemical growth and more aggressive corrosion. So that's a kind of thing that really goes to the design of a well. And what I find that we need to do as well designers is not only assume that we're going to have a long use of the well, it's going to meet and exceed the demand, but also to give options for rehabilitation. What if the regional water table drops? What if water quality needs change? All these sort of things. What if we just have a submersible pump that needs a shroud? Things like that. We need to accommodate it with the dimensions and depths and diameters and so on of our well.
We had a question here. So Alex asks, are there funding opportunities, federal or state, to bridge the gap between what clients would want to pay for low bid versus what is economical, sustainable, the higher bid for, I'm assuming, the difference between
Yeah.
the mild steel and the stainless steel. So,
Good question, Alex, and there are, so like here in Arizona, we have WIFA, which is the Water Infrastructure Funding Authority, and they use other USDA money, and there's grants from a lot of the feds these days. A lot of these federal grants for infrastructure are for water. They're either specifically for water or can be applied to water infrastructure, and so that's true. What I don't know is if such grants could be applied to, say, a guy that needs to deepen his household well, which that sort of thing is also a need out there, and I don't know for sure about that. But grants are available, many of them, and it's good. Both, well, it's usually from the feds, but through state agencies like WIFA and their equivalent entities in other states.
all right. So, based on my experience, I'm seeing a lot more acceptance of going the stainless steel route. And are you seeing that across the municipal markets in general? It seems to be an acceptance of that at this point. Like you say, some people they marry the mild steel upper casing and the stainless steel screens with a dielectric coupling, and I think that can save some costs too. But are we seeing more of a shift to that?
We are, and really, most municipalities and many industries are doing that around here. Now, I don't know if that's nationwide, but I know that around here, and I think that probably the suppliers, Johnson Screen and Roscoe Moss and all those guys could answer it even more broadly because they see it in a broader region. But I believe that it's just becoming more. People are seeing like, I don't want to replace this well every 25 or 30 years or 50 years. Even on those cycles, it's too disruptive. And what really augments that concern is if you think about a single well site, let's say you have an acre or two, you put the first well, the second well, the third well, maybe they're not exactly plumb and aligned. And so, now you have limited geographic area to put the next well. And so there's these problems that you begin to bump into. And I know of entities that have encountered such things. So we don't want to start painting ourselves into a corner that way, and have plenty of longevity to these wells and utility while they're being active, and so we can get that most efficient water out of the ground.
Okay. So, kind of my next question is, one of the assumptions in your life cycle analysis is doing the regular well rehab, and we know that reality versus theory here. A lot of people don't do their rehab until the well stops pumping. I mean, what I do with my clients is we kind of set them up on a where they're listening to me actually, which always a difference. But we set them up on kind of a KPI, a key performance indicator basis, where you're looking at things like specific capacity and some other factors that'll kind of document when they need to do their well rehab. But how do we break that thought where we're not doing, we can kick the can down the road, and we see that I think the data from well rehab studies shows that you push the well so far down the road that you do a rehab, and even a thorough rehab is never going to get that specific capacity back to where it should be if you did things regularly. So how do we
You're
change
right.
that attitude?
Yeah, that's tough. Because even though most folks that I'm aware of are being a little more proactive because they're recognizing the importance and value of groundwater, there are still those, and there probably will always be those that culturally just run to failure mentality, and they'll just wait till it's very far gone. And you can only do so much. You know, you can offer information, you can reach out to them, but if they won't listen, then that's going to be their option. And then if you go to a well that is extremely scaled or extremely corroded, you may not be able to save it, or the cost to save it may be equal to or greater than a replacement well cost. So now you're done. All you can do is explain how that's an avoidable problem. They could get more life out of a well, perhaps that sort of thing. But you know, it's not a it morphs from being a hydrogeology problem into a human nature problem, right? So if you can get them to listen, then that's where I like to draw cartoons in the PowerPoint.
There you go.
People don't want to see math; they want to see cartoons, and so I kind of trend that way.
Easier for people to grasp. So and kind of one of my final. Well, I got one more actually, but we saw during kind of the height of COVID when we had supply chain disruptions and everything, a lot of pre-designed wells because you were just kind of going into an area and you were trying to grab what you could in the way of supplies to keep things going, because we didn't know when we were going to get more screen. I mean, we even saw situations where we were getting disruptions on gravel pack and things like that. So people were buying this stuff up, pre-designing wells and buying the materials before they'd actually even drilled the well, which is taking a little bit of a risk. I guess if you're in certain areas, you pretty well know what you're going to get. But how does that affect your life cycle cost analysis, if at all? And maybe the pros and cons of the pre-designing wells. I did a show on that, a couple of years ago, but it's how does that factor in, if at all?
Yeah, the best way to design a well is to have either an exploratory boring in the immediate area or a pilot hole and gather site-specific data, because a well, unlike a bridge or a building or some other infrastructure, it is interacting with Mother Nature. Mother Nature isn't layer cake. If you're in an area where you have wells all around and you have abundant information and you're sure that it's not going to change from point A to point B, that's a real situation that sometimes happens. But there's other places, like in my area, where what geologists call a facies change happens. In other words, a sand unit pinches out, now it's a clay unit 100 feet away or 20 feet away. It can happen. So that means that if you assume that point A equals point B, you may or may not be correct. Well, with a pilot hole, we can know for sure. We collect cuttings, we do geophysical logging, we can do depth specific groundwater sampling and see if the water quality has changed. So we can design a well specific to that point on Earth. That's the best way to do it. If the situation doesn't accommodate that, and there's times where it doesn't, then so be it. But there, it's important for the well owner, the client, to know the risk. Like, okay, we don't know this, so we're designing this based on all this other regional information. We're extrapolating it in here. We may be right, we may be wrong. But that way they know that if it is less than optimum, if it doesn't perform as well as their previous well, or at least their memory of the previous well, then they'll know why. That they didn't pay the money for geophysical logging. They didn't have anybody log the cuttings, and so if there's only a driller hired, at least they're going to get the cuttings logged, because drillers, they're at least going to look at the cuttings they're drilling. but that's where they've already committed to it. They've already committed to a depth. They might have the screen material already on site, and that sometimes is a reality. It's not optimum, but it happens. So I think the best thing there is for us to just be sure that the information of that commitment is politely, conveyed to the client.
Yeah, and I go back to the fact that, what we were joking about earlier is that geologists are cheap, but
Yeah.
the value of having a geologist logging your hole, I mean, and you're both a geologist and a driller, so I guess, but I swear that sometimes these drillers' well completion reports are done in the bar after about 4 or 5 beers, and so sometimes they're, they get kind of creative sometimes. So, but
It's
in all
interesting.
seriousness, yeah,
Yeah, there's some that are that way, but there's also a lot that are incredibly impressive, especially from the years and years past. And so it swings both ways. And I can name out, but I won't, a few geologists that I don't know if I'd want to trust their logs. Were probably also done in that same bar.
yeah, exactly. So, that is true. But in all seriousness, the value, the cost, the value you get from having a geologist, a competent geologist, log your borehole is, it's paid off many times over, and you get good information, and we're really making some pretty expensive decisions,
Oh
based
yeah.
on things. So that it, so I'm not necessarily a fan of the pre-designed wells. I mean,
I'm with you.
but
Yeah, and besides the stainless steel well that I showed from 2011 being 700 something thousand, that's over a million. That's like 1.1, 1.2 million these days. And so, we're talking about an expensive piece of infrastructure, and the design should be consistent and it should be adjusted as you go based on the information that's gathered. That's what is a reasonable approach. That's kind of what I laid out in my book, and what I would advocate for folks for the reason of, if nothing else, just pure economics. But you can go beyond that. You're talking about water resources. So it really is critical.
well, that's all the questions I had. Any final comments, Mark? I will say that like I say, when I saw your talk in 2000, it really reoriented my thinking, and I've been promoting this concept ever since then, and trying to get people to understand it, and it's it really is revelatory, I guess, and so the work you put into it, I mean, that was a lot of work to do those calculations in that study, and it is much appreciated, I can tell you, and just an example of your contributions to the water industry, and so very
I
much
like,
appreciated. Um,
yeah.
and before we let you go, too, if there's, I know there were some problems with the comment section. So if anybody has any questions or anything for Marvin, you can post them to on LinkedIn or YouTube, and I'll get them to Marvin, and we'll get them answered for you, and go from there. I would highly recommend you, if you don't have it, pick up a copy of Marvin's book, The Art of Water Wells, and that's available from the National Groundwater Association. I don't think it's available on Amazon, is it, Marvin?
No, I don't think so. Just go
Okay,
to the TWA bookstore and they'll sell it to you. Um,
okay.
and if anybody has questions, I also am fine if they want to email me directly. It's just Glotfelty, like my name, at geo-logic.com. And shoot me an email. I'll be glad to do my best to
Yeah,
answer any questions you might have.
yeah, I'll post that in the show notes too, so people can get a hold of you. Marvin, thanks so much for your time. We really appreciate it, and on this very important topic. So, I will. We'll be talking later, and I'll see you at the National Groundwater Association in Las Vegas here in a month or so.
All right. I'll see you guys soon.
All right.
Thanks.
Bye now.
Bye bye.
Let me see where we All right. That was a great talk, and Marvin is just a giant in the industry, and as you can see, there's a lot of wisdom there, and we really appreciate that. So thanks everybody for attending. Sorry about the problems we had the with the comment section. I'll have to go back and look at that and fix that for future shows. But in the future, if you're interested in being a guest on Groundwater Talk Live, love to have you on. And this is the link to come on if you want to contact me directly. You have my email address also, so I gave that to you early in the show. And so thanks for watching. We do this every Thursday at 11 a.m. Central Time. Be sure to subscribe to the Groundwater Guy YouTube channel, and we will see you next week.